All right, so supposing we wanted to determine the value of this integral. This is a trigonometric integral that we can find the value of by using complex analysis. Okay, so what I'm going to do is I'm going to let z equal e to the I x. Okay, that means that dz is equal to I e to the I x dx. Okay, or dx is equal to dz divided by iz. Okay, and so that allows us to transform this integral immediately into a complex loop integral. Notice that unlike the integrals that took place along the entire real axis from negative infinity to infinity, in this situation, there's no need to add an additional part to make it a closed loop integral. It's already a closed loop integral because x goes from 0 to 2 pi. So that means z goes from 1 back to 1 after it goes all the way around a circle. So I'm going to integrate this along z equals 1. I'll have dz over iz divided by 5 plus 2. And now I have to write cosine x. Cosine x, of course, is equal to e to the ix plus e to the minus ix divided by 2. Well, that's z plus 1 over z divided by 2. Okay? And so this is the loop integral that we'll be doing. Now, this 2 cancels out. I'm going to pull a 1 over I out front. And I'll have dz divided by z squared plus 5z plus 1. All right. So I've got a loop here and my integrand will have issues wherever the denominator is equal to 0. So I'll have simple poles at -5 plus or minus the square root of 25 minus 4 over 2. Okay? Now, -5 minus the square root of 21 divided by 2 is way out here. It's not inside. However, -5 plus the square root of 21 divided by 2 is inside. So that means that this loop integral is equal to 1 over I times 2 pi I times the residue of the integrand at -5 plus the square root of 21 divided by 2. That's 2 pi times. All right, I'm going to do a residue. It's a simple pole. Okay? I can think of it as L'Hopital. I'll get 2z plus 5 in the denominator. 1 over 2 times this plus 5. And so this gives me 2 pi divided by the square root of 21. All right, I can do this in general for any loop or for any integral of this form, and I'll get using exactly the same process. All right. More generally, we can use this process to do an integral from 0 to 2 pi of any rational function of sine and or cosine from 0 to 2 pi. All right.